Hi, and welcome to another Hopper on 6502 video. This one is actually about a hardware project that I plan to get Hopper up and running on the 6502 in a way that makes it easy for other people to do the same. So what we're looking at here is a little, prototype for a single board 6502 machine. And I'll do a quick demo to show you what its capabilities are. And then I'll show you the background and why I'm doing this. So let's do a little demo. So I've loaded up this is the Hopper terminal connected via a serial port to the device. And I can, as I type text, you'll notice those blue LEDs are changing. So as I type, there you go. So if I type a backspace, that will be an 8. So you can see the fourth LED from the right is lit up because the right it's bit 3, so the right handmost bit is bit 0. A space would be 32, so that should be 2 further along. A 0, if I type a 0, I should get 48, which would be 32 plus 16, both of those. If I type an ampersand, we get 64, so that should be the next light to the left. Anyway, you get the idea. And then the LEDs that are counting in binary there, the yellow ones, are actually counting in seconds. So I have a timer on one of the peripherals that I can get accurate time, well, accurate relative to the clock speed. And then another thing I did with the device, let me switch back to the larger view, is unlike my earlier design, which I'll show you in a second, I didn't have a non-maskable interrupt button, so I do on this one. So if I hit that, it'll clear the yellow LEDs. So all that's doing is writing a 0 to that port. So those are like GPIO pins. Anyway, let me do a quick summary of what this is all about. Let's do desktop with no video. So almost exactly a year ago, I built a single board 6502 to run Hopper on. My work definitely, I was inspired by Ben Eater's machine. And Ben Eater sells a kit to do breadboarding. Ben Eater's design includes an LCD display. He also added a PS2 keyboard at some point. His design is very similar to Grant Sill's design. I'm pretty sure that most of these designs out there are similar, but there are differences. And in both cases, they use a serial port, an actual RS-232 serial port with a MAX32 chip on the other side of their UART. I did something very similar in mine. So I've got the LCD. I've got a PS2 port on here with these TTL chips for the PS2 driver, much like Ben Eater's design. I've got an actual RS-232 card in here with a MAX32. You can see the little capacitors there from the MAX32. And I've got an independent power supply here as well, which they all pretty much have as well. So what I wanted to do with this one was I wanted to fix some of the mistakes I'd made in my version a year ago. And I'll post a link to this process I went through building this machine a year ago and getting it onto a PCB and all that, testing it and bringing it up and what I learned. And at the end of it, I posted all the mistakes I made. Somewhere at the end of this, there's a list of mistakes. Here we go. Summary of blunders and what I learned. So I had said I was going to get back and do another one. And after I got Hopper running up and running on this machine, I almost never used the LCD. And I certainly never used, I've got this, RC 2014 micro keyboard that I made, a PS2 keyboard. And this one here, I never used this either. So I decided that in a rework, I wanted to keep it as simple as possible. So I wanted to build a simpler machine with less components, I wanted to make it so that you could just order the board from one of the online PCB manufacturers and build it yourself. I've got, my eyes are not that great. My hands are a little wobbly, so I don't want any, I want them all to be through-hole components. I don't want anything finicky. I don't want any surface-mounted stuff. So I figure that's, those are kind of good objectives. Most of the other designs use a single clock for both the serial and the, so here, Grant Searle's design, he's got a single clock that he divides so that he can use it for his serial chip and for his CPU. I wanted to keep that simpler in this version, and I wanted to also keep the 6502 maxed out and have a easy frequency for RS-232 over here. So I'm just going to use two CAN crystals instead of one. Just to make the design simpler. Most of these designs use TTL chips, 7.4 series TTL chips for the address decoding. I've got an article I published in July last year about using a CPLD for address decoding. And once you've got an EEPROM programmer to program your EEPROM, you can use your EEPROM programmer to program this thing as well. And they're fun things to learn how to use. One of the benefits is you don't waste a single byte of memory space in the address range. So in my case, let me see if I've got that handy. Yes, I do. When I look at, this is my map of the 0 page of my RS-232 machine. And down at the bottom in the light blue is where I've mapped the port. So this is my VIA port, is mapped to, it's got 16 registers, it's mapped to 16 bytes in the 0 page. And my serial port only actually uses 2 bytes, but I've got 4 bytes mapped in case you use the other serial port, the, what's it called, 6551 or something like that. Whereas I prefer the Motorola one because it doesn't have that bug in it with where the one flag doesn't work. The Motorola one is really easy to work with, and it's only got two registers. Actually, it's got more. It's got 3 registers, but one of them is read-only and the other's write-only, so they share the same address. Anyway, one of my motivations was to be able to map them to the 0 page, so I can map my peripherals to the 0 page without wasting any address space by using a CPLD. Once you map them to the 0 page, I talk here about other ways you could do address decoding. Once you map them to the 0 page, you can use these extra instructions that are available on the Western Design Center version of the 6502, the ones with the extra instructions. So you can use these bit instructions on the 0 page, which makes it really easy to code your interrupt service routines and smaller. So you save space. I sort of do a little study here of how many bytes it is with and without using these instructions. So the benefits of using the 0 page, so you can make things smaller and faster. I also just think it's elegant, it's neat, and you learn to program one of these devices in the process. So you can program it with your regular EEPROM programmer if you already have an EEPROM programmer, which you probably will have if you're playing with these sorts of things. Anyhow, one of the other things I wanted to get right in this version was to add a, like I said already, an NMI button, so that this will clear those little yellow LEDs. As I hit the NMI button, it should clear the yellow LEDs. There they go. Then they start counting up in seconds again. Hit it again, they clear. So that's me testing that my NMI is working the way it should, which it should. It's not that hard. And then the other thing I wanted to perfect was reset. So it's a power on reset as well as just hitting the reset button. And I wanted to have a super clean reset. And the way I do that is with this little chip over here. Well, you can barely see it. This little, it looks like a transistor, but it's not a transistor, this guy here. And you can see both, I've got an 8 megahertz CAN crystal, and I've got a 1.8 for the serial port. Anyway, let's talk about that reset. So the other person I got a lot of good ideas from is Garth Wilson, and he has a site with a lot of detailed explanation of why to do things certain ways for the 6502, and there's a lot of good value in his documentation. it takes a lot of effort to actually document things well. It's easy to do what I'm doing right now and just make a video. But to do what Garth's done here is really great. So he talks about using these chips here, the DS 1813s, for doing it's both power on reset and a reset. When you hold the button down, and what it really does is it gives you 150 millisecond delay where it holds the reset signal low. And that reset signal is connected to all your peripherals as well. So it's connected to the VIA and it's connected to the UART as well as the CPU. So that it holds that signal low long enough for all of them to get their story together before they start. So the 6502 needs about 25 cycles on its clock cycle before it can be ready to go. And 150 milliseconds is way more than that. And then the same is true for the peripherals. It gives them time and it allows the power to come up on power on startup so that it's at a good level, around about 5 volts before anything starts to work. Right, so let's have another look at the circuit and see what's in there. So I think there's about 6 chips now. Let's see what we got. So this is the CPLD, so that's doing the address decoding. This is the 6502. This here is the ROM. This is the VIA, so the Western Design Center 6522. This here is the Motorola 6850, which is my favorite UART by far. So 6850, the VIA, ROM, CPU, and this thing here is a 28-pin RAM chip. I prefer this form factor, but I just bought these ones by mistake. But it made me think that I should, on my PCB, maybe make it so that you can have so the PCB supports multiple layouts. So if you get a narrow RAM chip or a wide RAM chip, the same is true of the CAN crystals. So if you get a small CAN crystal, like a little, it's about the same size as a regular 8-pin IC versus this one, which is the size of a 14-pin IC. So on my board, I might lay it out so that it doesn't matter which components you can get, because these things aren't always as available as we'd like them to be. All right. More about, so what I got running right now is a test app. So let's go have a look at that. Let's switch to that. So we're back in here. I'll exit out of my terminal. And now we're actually in the Hopper environment for the first time in this video. So I try to write the simplest possible. This is my 6502 assembler in the Hopper development environment. I've got a whole video series on this that I'll link to at the end. But this, to me, was the simplest way I could test all the peripherals. So I'm initializing the Hopper stack because I'm going to use it later. Initializing the VIA, initializing the serial port. Setting both the 8-bit ports on the VIA to output. Now, I didn't actually, I wasn't going to include it. I was going to only have 5 chips. But then it occurred to me that I wouldn't have my time functionality. So I actually added the VIA back just for the timer. I could have used something else like a Riot chip for that. But, and then once I added the VIA chip back, I thought, oh, great, we've got 16 GPIO pins. So, I quickly came up with the, is it even here? No, I came up with a GPIO library in the minimal runtime as well, so that, Arduino style, you can connect things to your GPIO pins. So what do I do to test? I check if there's a byte available from the serial port. If so, I read it, and then I write it out to the blue LEDs on port A. So that's why we were seeing the different characters light these LEDs up. And then I echo it back to the console. So that's why when I was typing, you were seeing the echo coming back. I then call an API to ask what the time is in seconds, which has given me the amount of seconds since we switched the machine on, or at least since the VIA started counting time. And the way I've got that set up is the way Benita had it, which is to every 1,000 microseconds, so every 1 millisecond, it fires an interrupt. And then this is a Hopper API to get the time in seconds, and so it's got to pop it from the Hopper stack, which is why I needed to initialize the Hopper stack. and then I put it out on port B, which is the yellow LEDs. So we see in the bottom 4 bits of that as it counts up in seconds. You can see them counting there. So the non-maskable interrupt handler is over here, and all the non-maskable interrupt handler does is clear those ticks, which is, these are consecutive bytes in the 0 page for a 32-bit count of milliseconds since you turned on. And then the regular interrupt handler, which is handling the interrupt from both the serial port and from the VIA. So if we go and look at the timer one, for example, here it is using those 65CO to S instructions, the bitwise instructions. So checking that it was its interrupt from the VIA, checking that it was the timer interrupt. The way you reset to start another run on the timer is to read the low word of the timer counter, increment the tick, and then it just cascades through here. Like if this one wraps around from 255 to 0, it'll increment the next tick, etc., etc. So this is how I'm incrementing a 32-bit value like this. So, I mean, if you've ever coded in 6502 assembler, you can see that this is slightly different to what you're familiar with, and it's a really comfortable way to code, especially if you're spending most of your time switching between 6502 assembly and another programming language like C or Hopper or C#. What are we looking at here? Just initialization, and I've got like the various different delays that you're going to need depending on what your because the VIA is working on your clock. So to count the correct number of ticks to get you your 1 microsecond delay, this is the arithmetic that's again, this is Ben Eater's work when he demoed it. So that's how you set up your serial port. I mean your VIA. The serial ports, I support different serial chips. So I've got a sort of generic wrapper here that works with all of them, and the generic wrapper handles a 256-byte buffer. Again, it's Ben Eater's version of it. I don't know his design of this circular buffer, 256-byte buffer. So if the read and write pointer are not the same, it means you've got a character waiting. So your is there a character available? All it does is compares the read and write pointer. I made a modification. This is the reason I implemented the NMI button, because I wanted a break button, because when I'm trying to break in Hopper and press Control-C, I had to add all this functionality just to make break work. So what I do is if you hit Control-C, it won't put it into the buffer. It'll actually set a flag instead, which means your Control-C won't get caught behind other characters in the buffer. It's treated as a special case. But now we won't need that anymore. Once now that I've got NMI working, I can use NMI as a break button. Like if you've got a basic implementation running in Hopper, which is what I had, it'd be nice to have a break button. Just hit a button to break. It's much easier than trying to like suppose you're outputting a whole bunch of serial, or you're inputting in the middle of you're typing and it didn't get all your characters. It's halfway through your buffer and for some reason it got stuck. You want to break and debug what went wrong. It's kind of nice to have a break button. And like I said, I do support other serial devices, but then this is the device I'm supporting right now. So it'll have its own interrupt service routine, and it'll look very much like the VIA's service routine. Where is it? Oh, this is it here, because I've got two versions. One for the 6502 with all the instructions, and this is what it looks like if you don't have all those instructions. So you've got to push A and pop A. Whereas with the one that has the extra instructions, for most of the times you come through here, you don't have to push and pop A because you're just doing these bit instructions that don't affect anything except themselves. And I do need to use A here, and I use X here. So all it does is it's putting, if it's Control-C, it's setting a break flag, and if it's not Control-C, it's putting it into the buffer. Well, there you have it. That's what I'm building. So I'll do another video after this one once I've designed the board and sent it off for manufacturer. I'm hoping to do it in less than the minimum size to keep the cost down on the board. I think it's less than 10 by 10 centimeters. And oh yeah, another thing. I don't want to have an independent power supply, so I'm running straight off this FTDI device here. So on the previous version, I was converting to RS-232 and then converting back again with this, like a dongle that supports RS-232 over USB. So it's kind of pointless. So you might as well just not, you have one less chip in your board if you don't have the max 32 to convert to RS-232 voltage levels. You just connect your UART directly to an FTDI device like this. And they're cheaper than the RS-232 dongles as well. And I also verified I can get 600 milliamps out of this, and I'm chewing much less than 600 milliamps. In fact, those LEDs are probably chewing more power than the chips are. It's ridiculous. Yeah, that's your limitation. Don't put too many LEDs on your board. Yeah, there we go. So I'll get this up and sent off to a board manufacturer next, now that I've got it all working. Yeah, while I'm waiting, I'll get the Hopper minimal runtime running on it quickly too. That should be pretty trivial. Maybe I'll do another video of that while I'm waiting for my board to come from China. Very good. If you're interested in one of these boards, let me know. I'm trying to make as simple as possible a board that's easy to assemble, so nothing finicky, and easy to source the parts for. So I'm not trying to make the cheapest possible board. I'm just trying to make the most practical possible board. In other words, can you actually get these parts? And I've been sourcing them from various suppliers, and I'll list the ones that I've been most successful with. So thank you for watching. And I suggest you go and watch, if you haven't seen my other 6502 videos that I did recently, go and watch that playlist if you're interested in this.